Everybody. This is Electricity and Magnetism course, chapter 28, Source of Magnetic Fields. The magnetic field will be given by this expression, mu0/4 pi qv cross r unit vector divided by r square. This is a given expression. We will use the applications of this, but we will not derive this equation. But it states that if there is a charge moving with some kind of velocity, it produces a magnetic field, and this magnetic field at any point is given by this expression. Here, mu0 is magnetic permeability. Its value is given as 4 pi 10 to the minus 7 Tesla meters divided by amperes. And but there is also another property that we remind you. Epsilon 0 was the dielectric constant, remember, from electric fields, and mu0 is the magnetic permeability. So the product of them is just the inverse of c squared, which is the speed of light squared. And don't forget, speed of light is 3 times 10 to the 10 meters per second, which is a very big quantity. So 1 over epsilon 0 mu0 is extremely small, okay? Very small, less smaller than 1, okay? Because usually the velocities are not comparable to the speed of light. Okay, so now let's solve an example. The application of this equation. We are in this example, we are assuming that there are 2 point charges moving. One is in minus v direction, minus x direction, okay, and the other is moving in plus x direction. Okay, so now the question is, when these 2 point charges, say 2 protons, okay, protons moving in opposite directions, what are the forces that they affect each other? So what kind of forces that they will be feeling due to the other part? So the force will be exactly the same for both of them. So if you can find the force on the top one, for instance, it will be exactly the same force for the bottom one, okay? Because their velocities are the same, and the distance here is given as r, okay? This is x direction, this is y direction, okay? And z direction is outside the page, okay? Anyway, so now what we do is that because these 2 charges are positive, plus q and plus q, okay, they will repel each other, so that electric force will be in upper direction. So let's look at that. So F electric will be, for this plus charge moving to the left, electric field will be in y direction. What about the magnetic field? The magnetic field, for the magnetic field, we see that it will be in, again, in the same direction, because velocity is in minus x direction, so velocity is in minus I direction, cross r. R now is the distance that, r is the distance, okay, v cross r, but r is the, okay, so r is this distance, okay, let's see, r is in, v is in x direction, but r is in y direction, j. So this is v cross r, okay, okay, j direction. So magnetic field will be in I cross j in minus z direction, basically, right? In minus z direction. So here, the magnetic field at this point, due to this charge, will be, because the charge is moving this way, okay? So if you do this, okay, if you do that, the magnetic field will be totally in z direction. So it will be, the magnetic field due to this one will be in upper direction. So in this case, F Lorentz force, which is QV cross B, okay, V cross B, V is this way and B is that way. V cross B again will be in upper direction. So the magnetic field direction also will be in the direction of the electric field. So both electric field and the magnetic field forces will be in upper direction. So we will use this expression to solve magnetic field and insert here and cross multiply by that. And as you see, all the angles are 90 degrees. So we see that this, first of all, the electric field force is K Q square over R square, okay, which is 1 over 4 pi Q square over R square. But the magnetic force is just QVB, but B is given by this, mu 0 over 4 pi, okay, QV divided by R square, okay. We have this result. We have this result. Now, if we now multiply, okay, so anything canceling? Nothing, okay. So force, if we divide Fe by Fm, the result will be equal to simply 1 over epsilon 0 mu 0 times V square. See V square there, okay. So it's nothing but C square over V square. So the ratio of electric field with magnetic field, ratio of electric field to the magnetic field forces is given by C square over V square, which states that Fe is equal to C square over V square times Fm. So as you see, Fe will be much greater than Fm because this ratio is extremely big. Whatever the velocities you have, as far as it's not close to speed of light, which is impossible for any matter to move in speed of light. So the speeds will be always much smaller than speed of light, but maybe close to speed of light, but not exactly equal to. So that's why we see that in all the cases, the electric force will be much greater than the magnetic force. Okay, so having stated this, we would like to now derive an equation for current carrying conductor. Okay, so when a conductor carries a current, okay, of course there is a little bit region dl vector, okay, and inside there is dq, and this produces a magnetic field, and the magnetic field will be circular due to this current of this wire. And let's say that this wire has a thickness, okay, like that, and the cross-section area is A, cross-section area, okay, cross-section area. Now, suppose that in this dl, this little distance dl, there is dq, okay, and dq is just n times q, okay. So now n times q, but now we define as the number density, which is n divided by volume, okay. But the volume of the cylindrical case, this one here is the volume, is just A times dl, because the distance, the height of the cylinder is dl, but the cross-section area is A, volume is basically that. So if you just put everything together, you see that dq is equal to nqa dl, okay? We did this kind of calculations earlier. So dB will be equal to mu 0 over 4 pi from this, okay, q, dq times drift velocity, this drift velocity, times sine phi. This is the angle between the velocity and the r vector, okay. This velocity is in this thing, in this direction, okay, and the angle is right there. So this is coming from the vector product. The magnitude of this vector product requires a sine phi, and everything divided by r square, of course. Now, if we include these things, and also say that this, if dq is given by nqa dl, we see that the current is just n over v, okay, q over t, L over t is the velocity, q there, and area, okay. this L over T gives you current, and LA gives you volume, which cancels that. Q over T is current, N times current, okay? So N times current will give you total current. So basically, using this, putting this into here, and using this, we can see that the magnetic field will be just simply given as mu0 over 4 pi, okay, times I dl cross r unit vector divided by r squared, okay? So this is Biot-Savart law. By using Biot-Savart law, we can calculate the magnetic field using this integral, okay? If you integrate the whole thing, you will get the magnetic field distribution due to current in any direction, and the direction at which the magnetic field is obtained is also arbitrary, obtained by arbitrary vector r. So this is a very general formula, but which is not easy to apply. Okay, so Biot-Savart law shows that if there is a current passing wire, then the magnetic field due to it at any point is given by this expression. Now we will solve some example as the application of this. Okay, so now we are putting now here the Biot-Savart law is B0 mu0 4 pi times I dl cross r unit vector divided by r squared. Don't forget this r unit vector. R unit vector is always defined as r vector divided by its magnitude. So if in case that we need, we have to use this property. Okay, so now let's see what we can do with this wire. Suppose we have a wire like that in y direction. This is the x direction. Okay, the current is passing through positive y direction, and say this is dl there. Okay, and inside there is dq, and this produces a magnetic field at this point. Okay, using right-hand rule, probably inside the page, so it will be dB, okay? It's always using right-hand rule. If you put your thumb in direction of the current and use your fingers, the fingers show you the direction of the magnetic field. So on the right of this wire, as you see, the magnetic field is downward, but on the left, it will be just in the opposite direction, which is outside the page. So what we do is that we just now, the current I is passing through here, okay? When we say that this is angle phi here, angle phi. If this is angle phi, then this is angle pi over pi minus phi, okay? Due to the property of the triangles. So if this phi, this is pi minus phi. But we know also that sine pi minus phi is equal to sine pi cosine phi minus cosine pi sine phi, which gives you this is 0 automatically. Cosine pi is minus 1 is minus sine phi. Okay, minus sine phi. Okay, but there is a minus sign here, so it's plus sine phi. Good. So what about cosine phi? Doesn't matter, we don't need this because you will see now why. Because r unit vector will be given as just sine phi, because if this is r, it has components, x and y components, okay? So y component will be downward, but x components will be this way, so that the x component is just obtained. This is Rx, right? Rx, right? Rx is just r cosine pi minus phi, okay? Because this is the angle we have. Now, Rx is this, Rx is just sine, okay? Sine here. This is the reason that we obtained that. And since Rx is r sine phi, the unit vector will not include this r because everything will be divided by r and r's will cancel. And then we will just simply have sine phi I plus something j. I don't need to calculate this, and you will see the reason why. Because dy now dl vector is just nothing but dy j unit vector. But if you multiply dl by r unit vector, it will be given as dy j cross r unit vector, which is just sine phi I something j. The reason that I didn't have to calculate is because j cross a gives you 0, so that no contribution from this. And j cross I gives you minus k, and as you see, minus k shows you the direction of the magnetic field, which is down, okay, inside the page. So it's minus dy sine phi k unit vector. So we know that the magnetic field will be downward, so with minus k unit vector. So the magnitude then will be, the direction is known, the magnitude is just mu0 over 4 pi times I dl cross r gives us this dy sine phi divided by r square. And I, being constant, can be taken outside. As you see, this is an integral with respect to y, but it's very difficult because sine phi is given as sine phi is x over r. We can do that since this is x and this is y. Sine phi is just x over r, okay? Because sine pi minus phi is sine phi. That's why it's automatically given by x over r. And now r has also y in it. So this can be written as, okay, mu0 I over 4 pi, okay, dy x over r, but there is another r square, so our cube root of r, which is x squared plus y squared, cube root. Okay, as you see, this integral is not easy, okay, because this is a y integration, but there is no y on the top, so we cannot use change of variable technique. So we have to use mathematical tables, which is not going to be easy. But there is another shortcut, okay? So we now turn this integral into an angle integration, okay? So how can we do this? How can we do this? We know that sine phi coming from sine pi minus phi, sine phi is just x over r, and tangent phi is nothing but x over y. From this, I can say that y is equal to x over tangent theta, tangent phi, okay? And this equal to x tangent phi to the power of minus 1. So if you want to get dy from here, take okay, differentiate both sides. You will get x minus tangent phi to the power of minus 2, okay? This is the property of this. The derivative of tangent phi with respect to phi, which is 1 over cosine squared phi, and times d phi. This is how you integrate it. But when you do this, okay, when you do this, you see that you now have this minus sign. Don't forget the minus sign there. So that dy will be equal to minus x d phi divided by tangent square phi, okay, times cosine square phi. But since tangent is sine over cosine, cosines cancel, and it gives you minus x d phi divided by sine square phi. So after this tedious algebra, we found this. Now also we have sine phi. Don't forget, we have to put sine phi as x over r, so that this expression will give you b will be equal to mu0 I over 4 pi, okay, multiply by dy, but dy is this, minus x d phi, okay, and there is x, there is another x, dy x. No, we are not using this, but this sine phi, right? Dy sine phi, sorry. We are using this expression, okay? Dy times sine phi. I is taken outside. Dy is just minus x d phi over sine squared phi, okay? Dy is written, then sine phi there, and divide by r squared. Divide by r squared. But now we know that sine phi is x over r, but x square over r square gives you sine square phi. So we multiply this by x and divide by x. So that x square over r square gives you sine square phi, which really cancels this thing on the denominator. All you are left with is now with minus sign, b will be equal to minus mu 0 I over 4 pi x, okay, sine phi d phi. Sine phi d phi. Okay, now this is the result, but now the integral of sine phi is minus cosine phi, so the minus signs will cancel, so that the result is just mu 0 I over 4 pi x, just cosine phi, with some limits, of course. But now we, instead of finding this limit, now we write this cosine phi as just cosine phi as just y over r, right? Cosine phi is nothing but y over r. This is equal to y over r. Now, because we know the limits for y, because this in the problem it is said that this upper length is a and this is minus a. So the total length of the wire is 2L, 2a. Length of the wire is 2a. In this case, this b will be equal to mu 0 I over 4 pi x, okay? Cosine, instead of cosine, now we are writing y over square root of x squared plus y squared, which is r. Now the limits we can place from minus a to a. As you see, we took the integration, we obtained a result with respect to sine and cosine, but instead of trying to calculate what the angles are at these limits, we just change it to y, and then we put the limits for y. So this is really something that we can do. As you see, in upper limit we have y is equal to a, but in the lower limit it will be minus a, but there is another minus sign, so it will be twice as much as this expression where y is replaced by a. So b will be given by just simply mu 0 I over 2 pi x. Why 4 pi became 2 pi? Because there was 2a there, times a divided by square root of x squared plus a squared. So this is the magnetic field that is obtained, okay, due to the cable, okay, current carrying cable. When a is much greater than x, it means that infinitely long wire, then this expression is approximately a, because x is negligible, square root of a squared is just a, and it cancels a on the top, and the magnetic field just turns into mu 0 I over 2 pi x. So this is the result that we had obtained earlier, okay? So now we would like to give an example. You know, Earth's magnetic field, B field, changes from like 30 to 50, 60 micro Tesla, okay? So the magnetic field of Earth is within this region. Now, suppose that we have a cable, the current passes through a cable is given as 1 ampere. Now, the question is, at what distance from cable X, B is approximately equal to 50 microtesla. So that when you put a compass like that, you know, showing the north, and if you are close enough to this wire which passes through 1 ampere, okay, will be just changing its direction, because this will affect, this current in the wire will affect this compass. So how close you have to put this compass to the wire which is 1 ampere, okay, 1 ampere, so that the magnetic field that this 1 ampere produces exactly equal to 50 microtesla, so that it directly affects this compass. So by using this expression, so x will be equal to mu 0 I over 2 pi b, because, you know, x goes there and b goes to the bottom. If you put all the values together, 50 microtesla for magnetic field, micro being 10 to the minus 6, and 4 pi, mu 0 is 4 pi 10 to the minus 7, you see that this is just 4 millimeters. Okay, so when you are 4 millimeters close to this wire, which is passing 1 ampere, it produces a magnetic field exactly equal to the Earth's magnetic field, so that the compass will be really affected. Well, now, if you double the distance, then double the distance, the magnetic field intensity will also be doubled, okay? Because it is related to 1 over x, so the magnetic field will be about 25 microtesla. If you go further and further away, the magnetic field intensity will reduce, okay? And then after a few centimeters, the effect of this magnetic, this current will be almost negligible. But when you are so close to the wire, then the compasses will be affected. So if you have a wire and put a compass underneath, and if you pass the current, you will see the direction of the compass will be changed. Okay, so this is a very nice example with the magnetic field. Now we continue with the electric and magnetic flux. Okay, we learned how to obtain the electric flux if there is a charge, okay, inside a box. Let's say this is plus Q, and now we place this in a box like that. Doesn't matter if it is perfect cube or not. It's some arbitrary three-dimensional box. We know that this this charge produces electric fields, and at each faces of this volume, okay, at each faces of the volume, the electric fields will be going away, so that, as you see, these are area vectors. Area vectors always perpendicular to the surface. So if the angle is phi, then we can now talk about the electric flux. Electric flux times dA, okay, suppose this small area dA, okay, E dot dA will be given by, okay, Q enclosed over epsilon 0. This is Q enclosed. So it says that if we can find the total flux on each surface, total flux, this is electric flux, by the way, total electric flux passing through this three-dimensional shape, then it is Q enclosed over epsilon 0. If somebody hides a charge inside this box in which we don't see exactly what, okay, where it is, then we can find the magnitude of this charge by you carrying out this integration, okay? Of course, for the point charge, it would be easier if we had like a sphere. But anyway, so if you do the same thing for the magnetic field, suppose that we have now a smallest unit, which is north and south. As you see, the magnetic field doesn't have any monopole. This is monopole, electric monopole, right? But electrical monopole, but for the magnetic field, we have only a magnetic dipole. So this is the smallest element of the magnetic field creating charge distribution. So this is magnetic dipole. So there is no magnetic monopole. But because magnetic dipole produces the magnetic fields, okay, like this curve, okay, okay, so this is the magnetic field that is created by the dipole, okay. Now, if you place this inside a box like that, so some of the magnetic fields will be outside, some of them will be inside on the other face. So the amount of the magnetic field vectors that are going away from one face, from the faces, the total faces will be equal to the number of magnetic fields coming into the faces. So the total flux will be 0 because there is only not one-sided electric magnetic field, but it's all round, because this, for instance, when this magnetic field goes out from the top face, it goes down, goes inside from the left face, and so on, depending on the orientation of this magnet, of course. This is the reason that the magnetic field is 0. Okay, the total magnetic field, the flux, the total magnetic flux in this shape will be equal to 0. There is no monopole for the magnetic field. So This is no monopole condition in Maxwell's equation. So this is as you see, these equations are differential equations. If we write the integral equations, if you write the differential form of these equations, you see that you can get divergence of electric field. Divergence of the electric field will be given as rho over epsilon 0, rho being Q enclosed over volume. Okay, so this is Gauss's law. This is also Gauss's law that we learned. But now, if you convert this into differential equation instead of this form, you see that divergence of B will be equal to 0. This is the no monopole condition for the magnetic field. So this, as you see, the Gauss's law has some number on the right-hand side, but here it's 0, so that there is some differences in the magnetic field and the electric field distribution for the Maxwell's equation. This really brings a big difficulty in solving the full Maxwell's equations, where Ampere's law and Faraday's law are included also. Okay, so now we will solve an application example for this thing. We know that the magnetic field will be given as mu0 I over 2 pi x for the current carrying wires. Now, if we look at this two wires are oriented such that they are along x axis, and the current from one of them, I1, is upper direction, and here is inside the page, okay? And we assume that I1 is equal to I2, it's equal to I. Okay, so now if the center line is y-axis passing from center line, they say that the distances, okay, from the currents to the center is just d for both cases, d. And now this we put a point here, P2, and we put another point, which is right there, P1. It's 2d away from this current. Of course, you can see that the distance from this I2 is just 4d there. And then we put another point here on the right, and the distance is again d there. So this is P3. Now, what are the magnetic fields at P1, P2, and P3 is the question. So we would like to find out the magnetic field at this point, the magnetic right in the center, magnetic field on the right. Okay, just like we found the electric fields between the two charges or outside the charges, right? We did this for the electric field case, but now we place currents to get the magnetic fields. But now the direction of the magnetic fields are important, okay, because we have to now consider our right-hand rule, okay? So for I1, for instance, the current is up, so the magnetic field for this P1 will be downward. So this is going to be V1 due to this I1, right, downward, because now what will happen is that there will be circulation, and I'm not drawing this circulation not to get confused. But now look at this I2, because I2 is now going this. If you do that, okay, you see that on the left of this bigger circle, of course, the radius being 3d, okay, no, 4d. In this case, the magnetic field for this, due to this I2 will be just up, like that. So this is B2. Probably B2 is smaller than B1, okay, because B1 is nearer to this I1, and the currents are the same. Okay, so we have to be right careful with how to draw these vectors. But in the middle, so this is our point P1. So in the middle, both of the magnetic fields will be in upper direction. Okay, why? Because remember that this is I1 is outside the board. So now, if you do this, the magnetic field direction will be in upper direction. Okay, so it will be like that, E1 due to this I1. But now for this one, as you see, if the current is going down again, okay, again, as you see, if you put your thumb down, your fingers will show again the positive y direction. So B2 will be also in the same direction. Okay? So we put the vector signs there. So what about this point P3? In point P3, okay, the magnetic field lines are such that, for instance, for this one, okay, for I2, it's downward, okay, so this is B2 vector, but for this one, it's up, shorter probably, okay, this is B1, okay. So now we can write the values here underneath, okay, and we can decide which one is greater so that we see the direction of the resulting magnetic fields. Okay, here B2 is given as mu0 I over 2 pi. Now the distance from this is 4d, okay, 4d. We know the directions, that's why I'm not writing j or minus j, okay. B2 is this. Don't forget the currents are the same and we choose the same currents for each one of them. And B1 is mu0 I over 2 pi, in this case 2d. Okay? For this part, they are the same. Of course, the magnitudes will be exactly the same. B2 and B1 will be exactly equal to each other. Okay? Mu0, okay? Mu0 I over 2 pi d. Why d? Because the distance to the center point for both currents is the d. But now for this one, okay, B2 will be equal to mu0 I over 2 pi. Now the distance from the second current to this point is just d there. But B1, now the distance from this current to this point is d, 3d. Okay, mu0 I over 2 pi times 3d. Now by calculating these ones, you can see that here the magnetic field is just for P1, okay, the magnetic field is given as the total magnetic field is just mu0 I over 8 pi d, okay, minus j unit vector. So because it's bigger, it's going to be in this direction. So for P2, the magnetic field will be given as mu0 I over just pi d, because the summation of the two just gets rid of this two on the denominator, so that it's j, it's in positive y direction. For P3, okay, the magnetic field is given as mu0 I over 3 pi d, okay, in minus j direction. So, as you see, on both sides of this current distribution, the magnetic field on the left is downward, the magnetic field in the center is upward, and the magnetic field on the right is going to be downward. Okay, so this is the example that we solved. Okay, now we can go to the forces between conductors. Okay, forces between conductors. Actually, we had seen, okay, we will see that the two currents will exert some kind of forces to each other. So suppose that this is current 1 this way, I1, and current 2 exactly, okay, in the same direction, and the distance between them is just x. Now we would like to find the forces on each other. Let's consider the force on, what is the force on cable 1? Okay, so we've just considered it at this point. Now, as you see, if the current is passing through this way, okay, the magnetic field will be in this direction due to this, okay, so it will be like that. The magnetic field will be in the upper direction due to this. So this is B2. B2 is due to I2. So now, as you see, there is charge there, and then moving V, okay, with kind of velocity, or instead of velocity, we say this L vector here, so that if we know the magnetic field, then we can find the force on the first wire, which is given by IL cross B. But this B is due to B2, but this I1, right? This is the current of the wire itself, and L is the length vector, okay, on the wire, but B2 is external magnetic field, which is created by this current. So now, this is, now everything is perpendicular. We know that this is, now L is this way, okay, L is this way, B2, okay, B2 is that way, so that now if you put your fingers like that, and then just multiply by B2 like that, you see that the force will be inside the plane, okay? So the force will be this way. So this will be the direction of the force. Now, in this case, since everything is 90 degrees, we just get rid of this vector sign, and because sine phi is 1, because 90 degrees business, so that this will be given by just, so I can just get the, I know the direction of the force, but I get the magnitude. F1 will be equal to I1 times L times B2, okay? But B2 will be given as B2 because of this, like this, okay? Because of the current, the magnetic field is just given by mu 0. I2 in this case, because this is B2, you have to use I2 divided by 2 pi. The distance between them is now x. So now if you see that this is equal to mu 0 over 2 pi, okay, I1, I2 over x. So this is the force that cable 2 exerts on cable 1. But now, guess what? F2 will be exactly equal to F1. So, but in opposite direction, of course. The direction will be different, but the magnitude will be the same. So basically what happens is that if you just tie these cables from these points, or just put some kind of plastic circles so that the current is obtained by using some extra power supply like that, because of this force, the wires will be just coming, okay, towards each other. So they will get closer and closer to each other if both ends are attached to some holes like that. So these cables just attract each other if the currents are in the same direction. But if they are in opposite direction, we will see that the forces will be totally away from each other. Okay, this is the end of today's lecture. So we stop now.